Hello and welcome to this lecture on fundamentals of electric drives. In the last lecture, we are discussing about the slip speed control of induction motor. By slip speed, we mean the differential bit between the synchronous speed and the motor speed. So, let us see graphically what is the meaning of slip speed. The slip speed, as we have discussed in the last lecture, is the difference of the synchronous speed, which is omega ms, and the rotor speed, which is omega m. Basically, if we are operating at, let us say, this operating point, speed is omega m. The corresponding speed here is omega m here. Now, if this speed is omega m, the differential speed between the synchronous speed, which is omega ms, and omega m, this is called the slip speed. The slip speed is designated as omega SL. And as we have seen that if we have a constant torque load, this is a constant torque load profile, TL profile, and if we have a constant torque load, it intersects the motor characteristic at 2 points, point A and point B. Now, we can very well see that point A is a stable point and point B is an unstable point here. So, it means corresponding to point B, the operation will be unstable. So, we have to operate at stable equilibrium point, which is A, and that can be ensured by controlling the slip speed. This is what is called the slip speed. Now, we will still have the variable voltage and variable frequency control of induction motor. We will vary the voltage and will vary the frequency, as we have seen in the last lecture, but however, this time we will control the slip speed as well. So, let us discuss the constant volt per hertz control with slip speed control. So, we will be discussing constant volt per hertz control with slip speed regulation. So, we will be regulating the slip speed. Let us write down the equation for the current. Now, we know that the rotor current, ignoring the stator resistance, the rotor current IR is given as the voltage, applied voltage, divided by under root RR by S whole square plus XS plus XR prime whole square. So, what we have tried here, we have ignored the stator resistance. So, we have a approximate equivalent circuit, which is shown in the following fashion. So, this is our stator leakage reactance, the rotor leakage reactance, the rotor resistance, which is RR by S, and we have applied a voltage, that is V, per phase voltage, and this is the rotor current seen from the primary side. Now, what we do here, we change both the voltage and frequency by a factor of k. So, the voltage is now replaced by kV, the frequency is replaced by k into f. So, the voltage is changed to k into V and the frequency is changed to k into f. So, that V by f is constant. So, if we replace this by V by kV and f by kf, we get RR prime is equal to kV divided by under root R r square by S whole square. We have the reactances here. The reactances in this case are this. So, this reactance will have the frequency term. So, what we have in this case is that the reactance will be multiplied by this k square x s plus x r prime whole square. Now, what we do here, we divide the numerator and the denominator by k. So, that is equal to V divided by under root R r by k s square plus x s plus x r prime whole square. Now, usually the slip of the machine is quite small. So, we can say that r prime by k s is much greater than the reactances. So, we can say here that r prime by k s is much higher than the reactance x s plus x r, as slip is small. So, usually we have a small slip. So, since the slip is small, this is quite large. So, if we apply this approximation, what we get here is that is equal to V by r prime into k s. So, this is the expression for the armature for the rotor current. So, usually we have the magnetizing branch here. So, this is the magnetizing current I m, the stator current is I s. So, since the slip is very small, the rotor circuit is predominantly resistive circuit. So, this circuit is primarily a resistive circuit, because S is very small. So, if it is close to 0 or very small, this is very large value, or we can say that as S is small. So, since S is small, the leakage reactances can be ignored, the circuit is mostly resistive. So, the rotor current I r and the magnetizing current I m are in quadrature. So, we can write here that the stator current is equal to I m square plus I r prime square under root, because I m and I r are in quadrature. One is the in phase current, I r is in phase current, this is I r, this is in phase with the voltage V, and the magnetizing current I m lags V by 90 degree. So, this angle is pi by 2. So, we can find out the resultant of these two by taking the square root of I m square plus I r square. So, I m is mostly constant. So, the stator current will be constant if the rotor current is constant. So, what we see here, that the rotor current is dependent upon k into s, voltage is constant, V is given here, R prime is the rotor resistance. So, if we can keep k s constant, I r will be constant. Let us see the expression for the torque. The torque expression is given as 3 by omega m s. Since we are changing the frequency, we have to multiply here a factor of k into I r square into R r by s. So, we will substitute the value of I r square. So, that is equal to 3 by k into omega m s. I r is V square divided by R r prime by k s square into R r by s. So, if we simplify this one, what we get is the following. So, we have this k s here. So, that is equal to 3 by omega m s into v square by r r prime into k s. Now, here what we get here is that the torque is proportional to k s. So, if we want to keep the torque constant, we have to keep k s constant. So, we had already obtained the value of the current. So, that is equal to a constant into k s. What about the current? The rotor current is equal to again some constant into k s. This you have already seen. This is a constant quantity, and V and R are constant. So, the rotor current is constant into k into s. Similarly, torque is some constant into k into s. So, what is this k into s? So, let us try to see what is this k s. Now, the slip in this case is the synchronous speed, which is k into omega m s minus the rotor speed by the synchronous speed. So, this is the value of s, slip. So, what is this? So, k into omega m s minus omega m is called the slip speed. This is called the slip speed by k into omega m s, because this is the synchronous speed and this one is the rotor speed. This is the rotor speed, and the difference of synchronous speed and the rotor speed is the slip speed. So, we will take this k to the left hand side. So, what we get here is k into s is equal to slip speed divided by omega m s, or that is equal to omega s l into divided by omega m s. So, this k into s is proportional to the slip speed. So, if you want to increase the slip speed, you should increase k into s. So, in this case we can also say that this the torque is proportional to slip speed, and similarly the current is proportional to also the slip speed. So, these are important derivation that we have, that the torque and the current are proportional to slip speed. So, for a given slip speed, torque and the currents are constant irrespective of the frequency of operation. So, even if the frequency changes, if we maintain a particular value of slip speed, both the torque and the current will remain the same. So, let us summarize this. Hence, for a given slip speed, the motor torque and motor current have remain constant for all frequencies, for all frequencies below the rated value, below the rated frequency, because we have a different control after the rated frequency. So, this is the conclusion. Now, what happens beyond the rated frequency? So, if the frequency goes beyond the rated value, the voltage is no longer increased proportionately, voltage remains constant. Let us discuss about the situation when the frequency increases beyond the rated value. when the frequency increases beyond the rated value, so what we do in that case is, that is, for k greater than 1, when k equal to 1, the frequency is the rated value. When k greater than 1, voltage remains constant, V remains constant. We do not increase the voltage beyond the rated frequency. So, for k greater than 1, V remains constant. So, in that case, what is the current? V will remain constant here. We will again ignore the stator resistance. So, this is R r prime by S whole square, but the frequency is increased. So, we have k into x s plus x r prime whole square. So, if you simplify this, what we get here is the following. So, that is equal to V divided by under root R r prime by S. So, in this case, what we assume that the resistance R r prime by S is very large. So, we can ignore this, ignore the reactant with respect to the resistance. So, this is what we get here. So, this part is neglected, x s plus x r prime. So, we ignore this part with respect to this. So, in that case, what we get here is V by R r prime by S. So, that is equal to V by R r prime into S. Now, if we find out what is S here, S was equal to the slip speed divided by k into omega m s. So, we replace this S by omega s l by k into omega m s, I r prime equal to V by R r prime into omega s l by k into omega m s. Now, in this case, k is increasing, the frequency we are increasing, k is higher than 1. So, when k is higher than 1, we have to increase the slip speed, so that the current is maintained constant. So, therefore, omega s l is increased with k to maintain I r constant. Every motor has a rated value of current. Suppose we have a motor which has the rating of 10 amperes. We cannot exceed that rated value of current, lest we should damage the windings. So, the current has to be kept constant at the rated value. So, beyond the rated frequency, when k increases higher than 1, what we have to do is to increase the slip speed with k, so that the current remains constant at the rated value. That is what we are doing here, that when omega s l is increased, we have to increase k to maintain I r constant. Now, what about the torque? Torque is given as 3 by k omega s. The frequency is increased by a factor of k. The voltage is not increased. So, this is V square by R r square into omega s l square by k square into omega m s square into R r by S. So, here we have R r by S. S is again omega SL by k into omega ms. So, that we can replace here k omega ms into V square by RR, and RR will be cancelled. So, we have RR here, and then we have omega SL in the numerator. We have k square here into omega ms square 1 by S. So, 1 by S is k into omega ms by omega SL. So, here we have some cancellation. So, let us see what kind of cancellation we have. We have omega ms gets cancelled with omega ms here, and omega SL will go, we have just 1 omega SL. So, finally, what we get, and also we have 1 k here, and here we have 1 k. So, what we get finally is the following. We get here 3 V square by R R prime into omega SL by k square, and we have omega ms square in this case. So, omega ms square gets here. So, what we finally get is a constant k into omega SL by k into 1 by k. Now, this is an interesting derivation. So, we are basically keeping this omega SL by k ratio constant. So, this ratio is kept constant to keep the current constant. Now, in this case, if this ratio is kept constant, the torque is inversely proportional to k is increasing, and hence beyond the rated frequency k decreases. Let us plot the various parameters like power, torque, slip speed with the variation of k. So, let us plot all these parameters against k in the x axis. So, k is 1 here, and then we have some value of k may be equal to 2. So, this is the rated frequency, this is the base frequency. Corresponding to this, we have frequency is the rated value. Now, let us see that up to the rated frequency we keep the torque constant. So, torque remains constant. What about the slip speed? Slip speed is kept constant up to the rated frequency. What about the power? The power in this case increases. So, the power is the product of torque and speed. When we increase the frequency, the speed also increases. So, the power, the mechanical power increases linearly with k. And after the rated frequency, what we have to do? We have to increase the slip speed. So, slip speed is increased to maintain the current constant. Now, if we see the current here, the current in this case has to be maintained constant. This is IS, the stator current. And to maintain the current constant, in this case, we have to increase the slip speed with k. So, to maintain the current constant, we have to increase the slip speed is omega SL with k. So, as the frequency or small k is increasing, we have to increase the slip speed to maintain the ratio constant. So, we have to increase the slip speed to maintain the current constant with k. So, we reach still higher speed, which is 2 per unit, and after that we reach the maximum value of slip speed. So, after that the slip speed is maintained constant, and the current, if you maintain the slip speed constant, the current will decrease with k. So, if you increase k and maintain the slip speed constant, the current will decrease. So, the current will decrease beyond 2 because the slip speed remains constant, decreases with k like this. And what about the power? The power here remains constant after the rated frequency, because the power is the product of voltage and current. So, the voltage remains constant, the current remains constant, the power is the product of voltage and current. We assume that the power factor is 1, it is resistive circuit. So, V and I remains constant and hence the power remains constant. The torque decreases, because if you increase the value of k, torque will decrease beyond the rated frequency, and after 2 per unit the power will decrease, torque will decrease further with k square, and the current will also decrease. So, this is a plot for torque, current, Pm and omega SL, which are in the y axis against the per unit frequency, that is k. So, this is how the various parameter changes with per unit frequency k. So, when we are increasing the frequency, initially we have a constant torque region. The constant torque region is up to the rated frequency or the rated speed. So, this is called the constant torque region. Because the torque remains almost constant. From 1 to 2, we call this to be a constant power region. Because the power remains constant. In this case, the power is constant for this region, and beyond 2, we call this region as constant slip frequency region, constant slip speed region. So, the constant slip speed means the slip frequency or the slip speed reaches the maximum possible value. Now, we can exceed a maximum value of slip frequency, because if you see the torque speed characteristic in this case, this is the maximum value of slip speed that we can have. This is omega SL max, otherwise we will be entering into the unstable region. So, we have to limit the value of slip speed. So, we have constant torque region, constant power region and constant slip frequency region. So, in this case, since the slip frequency is regulated, the current is also regulated, torque is also regulated. So, this is a better drive compared to the open loop V by F control drive. So, we stop here for today's lecture. We will continue with this slip regulation in the next lecture.